Now, the next problem we're going to have here is number 81, and now we're starting with a weak base, and then we're going to titrate it with a strong acid. So our reaction looks like this. We're given the Kb value for this at 4.7 times 10 to the negative 4. We have an equivalence point problem again. So it's kind of the same thing, only in reverse, not reverse, but from a different point of view. So this is the reaction. This is going to be a weak base reacting with a strong acid, so it's a weak base, strong acid titration. And the fact that we are titrating with an HCl here means that we're going to get a pH of less than 7 this time, because we're going to end up with a weak acid. How do we know that? Well, the OH and the Cl are going to switch, or the H and this monstrosity right here are going to switch. You give us CH3CH2, NH3Cl plus water. And that is our weak acid. That has been, is the conjugate with the weak base right here. So, we can start doing some calculating. This is the weak base. We got 32 milliliters, which is 0.032 liters. To figure out the number of moles we have, we multiply 0.032 times 0.087 moles per liter. We cancel out, leave us moles. 0.032 times 0.087 gives us 0.00278. Moles, or 2.78 times 10 to the negative 3 moles. So we'll put that right there, 2.78. Okay, and because this is at the equivalence point, if that's the moles of base, then that also has to be the moles of acid. And now, to find out how much volume we have, we got to use that and that together. So we're going to go down here and do that. 0.150 moles per 1 liter equals 2.78 times 10 to the negative 3 moles over the volume of the acid. Okay, because that's our HCl. So we'll cross multiply and divide this. Negative 3 times 1 divided by 0.150. And we get 0.0183, or 5 rather. So VA equals 0.0185 liters. So we're going to put that right up there. 0.0185. That's the number of liters of the acid. Now the total volume is the sum of these two right here, which looks like it's going to be 0.0505 liters. The moles of excess, well, we know we have this, we know we have this, which is actually the hydroxide. So that means then that the moles of excess is still going to be, no, I'm sorry, that's the weak base. This is H positive right here. So we're going to get the weak acid as the conjugate there. And so that's going to be also 2.78 times 10 to the negative 3 of that acid. Now, to find the concentration of the excess then, we're going to divide that by the total volume, 0.0505. And we get 0.00550. moles per liter of the acid, but we can't find the pH from that. We have to find the H concentration, which means we're going to have to do a look at the reverse reaction because we have none of this left. All of this is gone, all of this is gone, and it's created 2.78 times 10 to the negative 3 moles of this. Okay, so now we're looking at the reverse reaction, because now we got nothing but water in that. So we got CH3, CH2, NH3Cl plus H2O yields, and think of that at the end of that as HOH. The H and the OH and Cl are going to switch, or the H and this are going to switch. It's going to give us CH3, CH2, NH3OH plus HCl. And that is a strong acid, and that tells you that you're running even Ka for this. The Kb was given as 4.7 times 10 to the negative 4. So this would be 1 times 10 to the negative 14 divided by 4.7 times 10 to the negative 4. And we get 2.13 times 10 to the negative 11th. Okay? Now the concentration of this, we said, was 0.00550. Minus X plus X plus X. And so this is going to be equal to X squared over 0.00550 minus X. So now we're going to plot form that. Negative X squared minus 2.13 times 10 to the negative 11th plus 2.13 times 10 to the negative 11th times 0.00550 equals 0. So there's your A, B, and C. So plot form it. Negative 1, negative 2.13, E, negative 11, and 2.13, E, negative 11, times 0.00550. And we get 3.42 times 10 to the negative 7 for X. Moles per liter. And that is going to be of your hydrogen ion because of this right here. That's your X. So we'll put that up there in the chart. The second part of this, 3.42 times 10 to the negative 7 moles per liter of the H positive. So now we take the negative log of that answer, and we get 6.47. All right, so that's number 81. 83. This one at least is not an equivalence point problem, so we just have to figure out what stage it's at. We have 500 milliliters of a weak base, so that's 0.5 liters. We have 200 milliliters of a strong acid, so that's 0.2 liters. 0.2 times 0.15 equals 0.030, and this will be moles of the strong acid. And 0.5 times 0.10 is 0.05 moles of the base. So this is a stage 2 problem, which means we're going to be using Henderson Hasselbach for this one. So the total volume is 0.2 plus 0.5, which is 0.7. The moles of excess, when you subtract these two, is going to be 0.02 of the base. And it's gonna, well, let's take a look at that, because this is one of those double step or double stage problems. So let's look at this reaction here. The NH4 and the H are gonna switch around. You got NH4Cl plus H12. So this is your weak base, this is your strong acid, this is your weak acid conjugate here. Okay, so we've got 0.03 here of the acid, we got 0.05 of the base. We know we're going to lose all of this, and we got 0 here, by the way. We're going to lose 0.03 here, and we're going to gain 0.03 here. So this is 0.02 moles of the weak base, and this is 0.03 moles of the weak acid. Okay, so we got 0.02 moles of the weak base, and then 0.03 moles of the weak acid. We are now going to divide both by 0.7 liters, and this is going to give us 2.86, sorry, didn't round off correctly. 0.286 moles per liter of base, and this is going to give us 413, that's it, 413 moles per liter of acid. Now we're ready to use Henderson Hasselbach. So pH equals negative log of the Ka. Well, we don't have the Ka, we have the Kb. So the Ka is equal to 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, which is 5.56 times 10 to the negative 10. So that's what we're going to have here, negative log of 5.56 times 10 to the negative 10 plus the log of the concentration of your base. Your base is 0.286 over your acid 0.413. And you should get negative log 5.56 E negative 10, close parenthesis, plus log 0.286 divided by 0.413, and you get 9.10. That's your pH. We'll put that up there in that one-step titration. 9.10. And there is your answer. So your practice problems are at the end of the script. Have fun.